Hey guys, I want to talk to you about the experiment that we did at the beginning of the semester when we were trying to find out how much citric acid, the sour flavor ingredient, there was in pixie sticks. So the first part of the experiment involved constructing a standard curve from known amounts of the thing we were trying to measure. So what we used were antacid tablets or Alka-Seltzer tablets. Each tablet had 1 gram of citric acid and a bunch of baking soda in it, so that when the tablet was put into water, those two reactants combined and made fizz, or carbon dioxide, the product of the reaction. So we were using this idea that if you have more reactants, you make more products in the chemical reaction. What we did was we used different numbers of antacid tablets so we would have different amounts of citric acid and measured the amounts of carbon dioxide that were made in each known reaction. So then we took that data and we made a graph. We plotted how much citric acid was used in each reaction and how much carbon dioxide fizz was produced in each reaction. And each point that we plotted had 2 values, one on the x-axis, one on the y-axis. The x-axis down here, the cause, and the y-axis over here, the effect. More citric acid causes more of the fizz to be made. So then what we had to do was draw a best fit line through those points, going through the origin, because if you have no reactants, you make no products. We used a straight edge and we drew the line that came the closest to going through all of the points. We expected it to be a straight line because as the amount of citric acid increases, the amount of fizz that's made should be proportional to the amount of citric acid, that these two things should increase at the same rate. If you use twice as much citric acid, you would expect to make twice as much fizz. If you used 3 times as much citric acid, you would make 3 times as much fizz. That these two amounts increase proportionally to one another. That gives you this straight line, a constant slope. Now the reason that we made this was so that then we could use that to find out an unknown amount of citric acid that was in some pixie sticks. The citric acid in the pixie sticks, we didn't know how much that was. So we poured some pixie sticks into a cup of water with some baking soda, and then the fizz that was produced, we measured that. When we did the experiment, we made sure to use more baking soda than it really takes to react with all of the citric acid that's in the pixie sticks. We used an excess amount, or more than enough to react, because we wanted to make sure that all of the citric acid reacted so that we would make all of the fizz that could possibly be made so that we could measure it. There was leftover baking soda in the cup, but we didn't care because we weren't measuring baking soda. We were measuring the fizz to find out about the citric acid. So if we knew how much fizz was made, that would be a value on this axis over here, the y-axis. If we know how much fizz was made, then what we did was we tried to find the corresponding value on the x-axis for the citric acid that it would have taken to make that much fizz. If we started with this much citric acid, we would have made that much fizz, just like we showed with the standard curve, known amounts of citric acid. So the reason I'm showing you this is because in the experiment that you're going to be doing for this project, you're going to need to construct a standard curve and use it to find out how much of an ingredient there is based on how much of a reaction there is. Now, there's another strategy that we used, the strategy of titration. In a titration, what we do is we use this analogy of walking towards the edge of a cliff and trying to find where the edge is by falling off. In a titration, the thing that we're trying to measure is how much of the cliff there is. In the experiment that we're going to do, the cliff is going to be vitamin C in apple juice. We want to know how much vitamin C there is in samples of apple juice. Now to find out, what we're going to do is add some drops of iodine solution, the titrant. Each drop that's added to the vitamin C reacts with the vitamin C and reduces the amount of vitamin C a little bit at a time, like walking towards the edge of the cliff. The thing is, we don't know where the edge of the cliff is, so in order to find it, what we have to do is add an excess amount of the iodine. We have to add more than it takes to exactly react with the vitamin C that's in the sample, But we don't want to add too much extra. We want to know where that edge is as close as we can. We want to have an accurate measurement of how much vitamin C there is. So we're looking for some indication that there's no more vitamin C left in the sample when we add some iodine. The indicator that we're going to use is starch. So as you're doing the titration, or as I demonstrate the titration, when we reach the end of the vitamin C that we're trying to measure, we'll see it turn blue. If you watch the video demonstration that came before this one, you can see how that titration looks. And I'll demonstrate it again when I actually do the experiment for you. We're just kind of reviewing some of the main ideas right now. So that's how titration works, just a quick review. So here are some things that you're going to need to prepare for the experiment. I'm asking you to do this on pieces of paper of your own. So you'll need some paper and you'll need something to write with. And you can label the papers just like you see me doing right here. If you need to pause and rewind and go back and look at that again, you can definitely do that. It's a video. So one set of data that you're going to need to collect are data for a standard curve. So label your data table standard curve data. And then you're going to have two columns of data. In this column, you're going to record the amount of vitamin C that is in some samples that I'm going to titrate. So you'll write down for each sample how much vitamin C that was. And then I'm going to titrate each one, and you'll need to write down how many drops of titrant it takes to reach the end point when I reach the end of the vitamin C and then the solution turns blue. So you're going to have several pairs of data. And then we'll plot those data on a graph just like we did with the pixie stick experiment. So this is one data table that you'll need to prepare on a piece of paper. And another data table that you're going to need to prepare. In the experiment, what I'm going to do is I'm going to cook some apple juice to find out what happens to the amount of vitamin C that remains in the apple juice after different cooking treatments. So one cooking treatment is going to be to change the time that the apple juice is cooked at 100 degrees Celsius. That's boiling. So I'm going to put some samples of apple juice in boiling hot water for different amounts of time. And then I'll show you how many drops of titrant it takes to reach the end point of the vitamin C to find out how much vitamin C is in each one of those samples. You'll need to use the standard curve graph to find out if this is how many drops of titrant were used, then this is how much grams of vitamin C were in the sample. And then you'll need to calculate what percentage of the vitamin C remains. If it's uncooked, the amount of vitamin C that's in there will be 100% because it hasn't been cooked yet. But we would predict that the amount of vitamin C is going to change as the cooking time goes on. We're trying to find out how does cooking affect the nutritional quality of food. So this is one data table that you'll need to make on a piece of paper. Another data table that you'll need to make looks very similar. You'll need to make the same looking data table, but this one is going to be about cooking the apple juice for the same amount of time, but at different temperatures. So I'm going to increase the temperature of cooking and do that for the same amount of time, and then I'll titrate to find out how much vitamin C was in each sample, and then you'll have to calculate how much remained after each one was cooked for the same amount of time, but at different temperatures. So we're looking at two different effects. One is the amount of time, and the other is the level of temperature. Okay, now you're going to need to prepare some graphs as well. You'll need to make 3 graphs. One is going to be the standard curve. So when you go to make the graph, you probably don't have graph paper at home. This isn't a piece of graph paper. What I do is I just drew 2 lines perpendicular there, and then I just marked 10 little marks on there equal distance apart. I don't know, how many inches or centimeters that was. I just marked it and then marked it again. It looked like it was the same distance each time, and I made 10 of them. I just eyeballed it. And then I did the same thing going up this way. So you can make your own graph paper that way. The first one that you'll make, you can label that one as the standard curve. And then what you'll need to do is label the axes. And this axis here, the x-axis, will be the vitamin C in the sample, how much milligrams of vitamin C there is. And then going up the y-axis, you'll need to label that one the number of drops of iodine titrant that were used in each titration. I'll show you what number to put here to scale the end of each axis, and then you'll need to divide that to make the intervals yourself, and then plot for each amount of vitamin C that was in the sample how many drops of titrant it took to do the titration. Draw the points and draw a best fit line, just like I showed you the way that we did it back in our experiment about the pixie sticks. Okay, another graph that you're going to make is looking at the effective cooking time on vitamin C in apple juice. So you can make the same graph. It's a different graph, but it's made the same way. And on the x-axis, we'll have cooking time. So I'll tell you what to put right here, and then you'll divide the scale accordingly. So I'll tell you the cooking time, and then you'll plot what percentage of the vitamin C remains after each amount of time cooking. The data that you're going to use for that comes from the data table that you made about apple juice that was cooked at 100 degrees for different amounts of time. This will be the vitamin C remaining. This will be the cooking time. Those are the axes on the graph that you're going to plot. And then you'll also make a graph that looks very similar, but not exactly the same. We'll have cooking temperature on the x-axis, because what we're trying to find out is the effective cooking temperature on vitamin C. This axis will stay the same. We'll find out what percentage of the vitamin C remains. The cooking temperature, I'll show you how to scale that one here at this end, and then you'll need to scale the intervals accordingly. And the data for that one comes from the experiment where we have the data for 5 minutes of cooking at different temperatures. So how much remains on the y-axis, cooking temperature on the x-axis. So these are some things that you can do to go ahead and get yourself prepared so that when I put the actual experiment video up next, you can record the data in the data table, and then you can use those data to plot the graphs. I'll put some more demonstration about how to do some of the calculations as we get to that part.